Our next speaker, Wolfram Buss, is coming up now, which is fabulous, and I'm sure that the presentation will appear here shortly behind me. Wolfram is working at the ANU, working on land-based carbon sequestration techniques, and he has a PhD from the UK Biochar Research Centre at the University of Edinburgh. And of course, therefore, he's going to talk to us today about biochar, and in particular, he's going to break it down into what it can and can't do, which I'm particularly looking forward to, and the role that it might actually be able to play in supporting sustainable farming in and agriculture more broadly within Australia. So over to you, Wolfram. Thank you.
Okay. I always have a bit of trouble getting into talks, and particularly today, because I wasn't really sure how I'm fitting in here. I'm not a farmer. I don't really have stories to tell because I'm a young academic. So I'm not a good storyteller anyway. So I wasn't quite sure really how to get into this. And the reason why I'm here is actually because in case there were border restrictions, I'm ANU local. I would have been able to come anyway. So I thought I do know a little bit about biochar. So luckily I do have something to tell. Yeah, so I thought I'd talk about how biochar fits into systems, into agricultural systems, and in particular the challenges around it. So the opportunities, but in particular the challenges, because I have been at lots of academic conferences, and there are people around that ask about biochar and about specifically why it hasn't taken off yet. That's one of the questions I get a lot, and I'll talk about this. So yeah, starting with natural charcoal. So the characteristics of charcoal is really that it's carbon rich, it's very stable, so it remains in soil for a long time. And that is really one of the key features. And in addition, it can help to improve soil properties. So that's really why we're looking into that, why we're so interested in that for agricultural systems. And so some of the most productive soils in the world, they have large amounts of natural charcoal in it. And here's an example of soils that actually have anthropogenic carbon in it. So essentially terra preta, that's how biochar has been discovered. Those are soils where char has been added by humans, and they are very productive. So we have this comparison of this dark soil that's really productive next to soils that are really decomposed, degraded in the tropics, and that are very unproductive. Now we're making use of this production of charcoal. So here I first have a little schematics on the left, essentially comparing combustion and pyrolysis. So in natural fires, we have a lot of oxygen present, and most of the carbon in biomass is actually lost. It's converted back into CO2, and we lose it. And only really like maybe 2.5%, obviously varies a lot, of the carbon of the biomass has been converted into char. Now, what we're trying to do is we maximize this charcoal production. So we minimize the oxygen in the system, and we're using high temperatures to produce charcoal or biochar. And that means we have some loss of CO2, but a lot of it is retained and is stable in the material. And then we have various different production systems. So we have either high-tech production, or we also have low-tech production with the right bottom corner. So there are really various ways of producing it. Now the definition, and that's really key, because biochar is different to charcoal. The production process is the same, but you can really use any sort of material, any sort of biomass to produce biochar. So here's an example of a picture that I took while in the lab at the UK Biochar Research Centre. And I was just walking around in the lab, and I was looking for some materials that we've used. And that's just a selection of it. So starting with straw, wheat straw, the left top corner, we had coffee cups, we had sewage sludge, then there's algae residues, the rice husk, pelleted softwood, and all sorts of material really that you can use. And then the definition is really that it's used for environmental management. So that's how it differs also from charcoal, because charcoal you typically use to burn, use to make energy from it, and biochar you use to either, for example, carbon sequestration or then putting it into soil and improving soil properties. So those are the key functions: carbon sequestration, soil fertility, improving soils, nutrient retention, water retention, also providing nutrients to the soil. So that's different to nutrient retention, and increasing the pH, so a liming value. Then there are 2-3 more functions, and actually a lot more. People use biochar for all sorts of things, and that's why the definition between biochar and activated carbon becomes lighter. It's not that clear anymore, because classically activated carbon has been used for soil remediation or for absorption of contaminants and nutrients from wastewater, and that's why I won't talk about those aspects. Another aspect is for livestock, so either as a litter amendment or to feed to give to livestock as a feed. So getting straight into why has biochar not taken off? So what are the key challenges? And here in Australia, really a key challenge is biomass availability. So if we're talking about carbon sequestration, we really need large amounts of material that we can actually use for pyrolysis. And that is a problem, in particular in a dry year. There is simply no excess. There is really not much material there that you can use in most areas in Australia. So that is definitely something, the first thing we need, key step, biomass availability. And the last 2 years, there was probably a lot of excess, a lot of stuff we could have used for conversion into biochar, but the previous years, probably not so much. And that also feeds directly into costs. So it's first obviously getting the biomass. So either if you have to buy it in or if you have to collect it, that's expensive. And in addition to that, the biochar production, the facilities are still really expensive. There are only a couple really sold, if at all, in Australia. Even worldwide, there isn't much production of biochar, so the costs are really high. And then the two at the bottom are basically linked, legislation and quality contaminants and risks. So this is one of those things. Legislation, as far as I'm aware, in New South Wales, it's still not allowed to actually apply it per acre. And yeah, contaminants is sort of the first aspect. I feel this is more of a perceived challenge, but I'm biased because my PhD topic was on contaminants in production and application of biochar. And that's a while back. So I feel that this is actually something we know a lot about and enough about to actually produce material that is really clean and safe. Okay, now getting into the first aspect, so carbon sequestration, and how does it fit in the opportunities? The key really is that it's long-term stable. So if you compare it to crop residues, and this is the comparison I'm making here, if you apply crop residues on the land, it's decomposed reasonably quickly. So the example here, obviously those values, 95%, that's really just a very generic value. That's the 95% of the carbon in crop residues is lost within probably a year or so. Depends, obviously, if you have a wet year, it's lost quicker. In a dry year, it can probably remain for a long time. And in biochar, basically biochar production, you have an initial loss of approximately, let's say, 45%. But then the remaining 55% of the carbon is really staying. It's staying either in the soil for a long time. It can also be leached out through the soil, but in the end, it's still the carbon in it remains stable. And that is the key. So it is essentially more efficient storage of plant carbon and also more reliable storage. And I'm doing research on soil organic carbon as well. So I'm not saying either or. I'm saying that in some cases, it makes sense to produce biochar from, for example, crop residues or forestry residues. In some cases, it makes sense, obviously, to leave it on the soil. For reducing evaporation, for example, absolutely no question. So it's not an either or. It depends really on the system, whether there is excess material that can be used. And why I'm saying more reliably is because sometimes, although we know a lot about soil organic carbon formation, sometimes we're still puzzled why we can't grow soil organic carbon. In some cases, one reason could be the last point here, that the system is saturated, which is unlikely in Australia. In most systems, it can build a lot more, but sometimes there is a natural saturation level where there isn't more to gain. And then biochar again makes sense because you take the carbon out of this natural cycle and have it as a different storage. The challenges really are, if you're a farmer, you probably don't have extra cash to just produce biochar, put it on your field just for carbon sequestration. So you want to be paid for it. And the emission reduction scheme methodology that was introduced, I don't know, 6-7 years ago or something, basically doesn't take into account. There is a method for biochar, but it doesn't take into account the carbon in biochar. So that seems a bit odd, but the idea there is that you can put biochar on your land, on your soil, to grow more soil organic carbon. So the biochar carbon is subtracted from that calculation. And that doesn't really make sense. And that's why you are actually not really paid for the carbon in the biochar that you put on your ground, on your soil. And there are hopefully some changes in the near future. And then there's obviously price. If you're just talking about the carbon sequestration aspect, carbon dioxide price in Australia peaked at around $55 per ton CO2. In Europe, it's currently at around 120. But if you look at the biochar costs, let's say roughly $1,000 of biochar per ton, which is equivalent to around 270 tons of per CO2. So we can clearly see that the production costs have to come down, and that is going to happen. As I said, there are only really a few units sold per year, if at all, in Australia. So once there is more demand and it's really taken off, then prices will go down. And we have to really reach that stage. Otherwise, yeah, it's just going to be too expensive. And then the biomass costs should go down. And obviously, the biomass costs as such will never go down, or unlikely. But this is one of those things that I'm researching on, is basically to get more stable carbon out of the same amount of biomass. So schematic on the right shows certain amount of biomass. You get a certain amount of stable carbon out of that. And I'm adding specific minerals to the process to actually enhance that yield. So to make the process more efficient. Now we're coming to the next aspect, and that's soil fertility. And I have divided that into water and nutrient retention and into nutrient provision, so basically used as a fertilizer. For water and nutrient retention, I'm really starting with the challenges. There is good evidence that biochar increases water and nutrient retention, but the problem is that there are large amounts needed to do so. So if you're looking at, for example, increasing water retention in a sandy soil, we did a meta-analysis, so we put all sorts of studies together and had a look across different landscapes, different soil types, how much biochar you would need to increase water retention. And that was more than 30 tons per hectare to actually change it. And there, that little calculation there just shows what the site preparation costs would be if you had a biochar cost of around $1,000 per ton. So we're looking at $30,000 per hectare. And then I have that other calculation down there, revenue. If you're actually making around, let's say, $900 per hectare per year, and Guy could make the calculation a lot better than me. Obviously, although it is a one-off preparation cost, you will never get that money back in. So that's why the sort of broad-scale application, sort of general application, doesn't really work. And it's very similar with nutrient retention. So if we consider that biochar is basically a bit similar to soil organic carbon, so this calculation is based on the fact that it can retain nutrient in a similar way to biochar, to soil organic carbon, and we're starting with a soil organic carbon content of 1%, and we want to reach 1.5. So we want to increase, we want to add 0.5% biochar to the top 20 centimeters. And according to my calculation, that would cost around $12,000 per hectare. Again, obviously, not really, it doesn't really make sense. So yeah, I started with the challenges, and now I'm coming to some sort of solution, some way how to at least make it a little bit more profitable. And one way is to have a root zone or banded application. So you can see in the pictures on the right, it basically means that you have it, instead of applied prod acre, you actually have around 1 ton per hectare prod acre, and that's in banded, so that you have 6 tons per hectare in that specific area where you actually applied it. it only reduces basically cost and divided by 6 essentially, but that would still be too expensive. But that's one way. And then another way is to actually use it for higher value crops. So something where you actually get more for your money anyway. So there are projects on avocado where then it makes a lot more sense. If you actually just increase the avocado yield by, a few percent, that is actually very valuable. And then you use also a lot less biochar because again, you apply it in the root zone. Another way is to optimize the biochar, to specifically tailor it, to change the surface properties. And this is something we do a lot of research on. With water retention, it's been difficult. So this is one of those areas where we haven't really progressed a lot. And the last aspect is really for long-term productivity. So either productivity gains or retain the productivity, because we know climate extremes are going to increase. We need to do something. We need to change the soil and make it climate resilient, really. But on the short term, I really see the opportunities mostly in this effect of biochar as a nutrient carrier or as a fertilizer. So that means you use a nutrient-rich material, something like manures, as we've just heard. Obviously, you would probably say that's not a good idea, but or sewage sludge, that is actually really something I've been doing quite a bit of research on. That is a nutrient-rich material. And here you can actually see at the bottom that what pyrolysis does is it removes organic contaminants in the material. And our sewage sludge is quite contaminated with all sorts of organic contaminants, and it needs treatment before you apply it on soil. So this idea of actually using pyrolysis to treat the material before you apply it, then you have a nutrient-rich but also carbon-rich material. That does make a lot of sense. Obviously, farmers would say, okay, where do I get the material from? In Australia, it is difficult because in the end, a lot of things are too far away from urban centers. So this really only makes sense in some areas. But there is a possibility of using nutrient-poor material and adding minerals to it, that either before pyrolysis or after. So for example, adding it to compost and then nutrient load it and then apply it. And then you have essentially a controlled nutrient release. There are specific coatings, carbon coatings on fertilizer that apparently are being sold now. And that also sort of controls the nutrient release. Or you can adapt it specifically, what I'm doing with specific minerals, to actually either have a more slower or more faster nutrient release. And the benefits then are that you can, you replace fertilizer. You use lower application rates than, as I've shown on the previous slides. And you have measurable benefits because you essentially have a direct incentive. You know exactly, how much fertilizer you're replacing, how expensive that would have been, what the effects are, because it's quite easily, you can calculate it quite easily what you're actually replacing it with. And then you still have the long-term soil benefits. And I've got that on this slide. So then the idea would be either a local sort of cycle of using minerals, sort of nutrient-rich materials, but also nutrient-poor materials. You process it then either on farm or a bit more sort of centralized facilities. You apply it on your land, and you don't actually bank on this sort of soil regeneration to start with, so soil fertility increase, but it's actually more about this fertilization effect to start with, and sort of long-term application. You then expect to have the soil regeneration aspect because you apply it every year, let's say in maybe a ton, maybe 2 tons per hectare. And you have, sequestration. That's obviously the other important aspect. It's not going to be a lot per hectare to start with in terms of CO2 sequestration, but if you do it year by year, you will have an effect. And then we have biochar really as a part of an integrated farm management system. So for example, if you have some forest on your land, for example, dead trees that you don't know what to do with the material, you can use that. You can actually produce some energy excess energy from something like wood residues, or also straw that you can feed into grid or use. You can feed it to your animals, and then the biochar is actually in the manure, and that helps again for nutrient loading of the biochar, for slower nutrient release. And then the other aspect here is essentially this plant, so sort of root interaction with biochar, where you then can increase, for example, the soil organic carbon formation that I mentioned previously, to basically have really a healthier system. That is actually then the last aspect, where biochar is just one part of an integrated carbon sequestration system. So you have, if you have, for example, a good year, you have excess material, above ground biomass that you don't know what to do with, you convert that into biochar, put that on the land. This helps to increase soil productivity. Here I've included basalt, which I didn't talk about, that's completely different, but crushed basalt can draw down and store CO2. It also provides minerals and liming, so increases the pH. And then you have really the idea of a system that increases soil productivity and soil organic carbon as a very important aspect here. So that's what I mentioned before. It's not an either or. You basically have specifically, if you have intercrops and cover crops and agroforestry, actually putting carbon directly, the roots putting carbon directly into the soil, improving soil organic carbon that increases water retention, and also a very important microorganism, the composition, to really have a healthier system. So that's then the goal, to really have one system that's healthier and that sequesters carbon. Thank you.
Andy. Thanks so much, Wolfram. So open to questions, please. They are deep seats, aren't they? Oh, John, you'll have to come and fight for it, I think. Oh. No, we'll, yeah, continue. Hopefully we can fit 3 in. We'll start with you, sir.
Thanks, Wolfram, for your presentation. My name's Rob Lawson. Do you think we need government incentive or legislation to kickstart the biochar industry? Because the way I see it, we have forestry, we have agriculture that, you know, lots of feedstock that's just getting burnt or oxidised. So that could be put into biochar and put it back into the soil. So do you think the government needs to kind of take a bit of proactive action on this?
Yeah, absolutely. I mean, that is exactly the thing. It does make a lot of sense in certain applications, and it does need to, as you say, it does need to be kickstarted. And that's the only way to do that. Is at the moment, it hasn't worked so far from the bottom up. So yeah, top down in this case probably makes sense to get some more incentives in.
Hi, I'm Patrice Newell. I was particularly interested in the slide you had where you said you had been doing research with sewage sludge, and the pyrolysis that you were using was removing the contaminants in the sewage sludge. So does that mean that the sewage sludge is wet? Does that mean that was a special pyrolysis operation that you were using that could do that? How did you do it?
Yeah, so essentially you do need to try the material before. Okay. So that's why the problem with sewage sludge is really the high moisture content. Absolutely. So to make it carbon negative, you basically have to have the water out of it first. So in this case, this is a waste management option that doesn't, as such, is not a carbon negative option, but it's better than the alternative, which currently is incineration, where you really get rid of all of the carbon in the material.
So does that mean that the sewage sludge as a biomass source coming in to be pyrolysed has actually been developed in that process of feeding in to be dried?
Essentially, yes. So we can use excess heat from the pyrolysis to dry some of the material, but in the actual pyrolysis unit, we need it at like around 15, 20, 30% moisture content only.
Thank you.
Well, just a little bit of trivia, and dung beetles come into this, of course, but research is being carried out as we speak. Biochar is being ground to certain sizes, minuscule sizes, and they've worked out what size the biochar has to be ground to so that it can be ingested by dung beetles. So they're actually putting very fine biochar in feed troughs in paddocks as well as dairy cattle. So the cattle are ingesting it. It goes through the animal. The dung beetles are then ingesting it and taking it underground, and all for free. You see, there we go. Yeah. By the way, after seeing how beneficial dung beetles are, I hope none of you ever again, when you're on a holiday in the country areas, ever again drive over a cow pad that's on the road. If you do so, you kill 50 of my dung beetles. And if I find out about it, you will go down.